Hi, I'm Shu. I'm a PhD candidate in Theoretical and Applied Mechanics program. These days, medical equipment is still very bulky. For instance, to get an electrocardiogram, a doctor has to put 10 electrodes on our body and then connect those electrodes to a big machine. For doctors, this process is laborious, and for us, it's uncomfortable. Other diagnostic tests can even be painful due to the large size of the equipment. Technology has advanced such that the latest iPhone in my pocket outperforms a laptop produced in 2015. In the same manner of miniaturization, can we replace some of the medical equipment invented 60 years ago with something smaller, portable, less intimidating, and more customized? One day, I was in the office searching for literatures. I came across a review article and was immediately attracted by the first image of this paper. Researchers have made tiny electronics in the laboratory, like a glucose patch that has the same functionality as a glucose meter, but is 10 times smaller, or a neural probe that can monitor our brain's electrical activities, or bacteria sensor for teeth. Moreover, all these electronics are made flexible so that they can be implanted into our body or attached on our skin for real-time monitoring with no or minimal damage to our tissue. How is that possible, I asked? How do they make silicon chips flexible and stretchable? The answer is that instead of silicon, they use polymer and a new type of material called two-dimensional materials. This name comes from the fact that they are extremely thin. In fact, all the atoms of two-dimensional materials are arranged in one layer, which makes them much more flexible than normal materials, like a thin sheet of paper versus a pile of paper. To me, these materials look so cool, but at the same time, from a mechanical perspective, they also look very fragile. We would like those electronics to work for as long as possible to reduce the cost and suffering for repeated implantations. But can they survive the dynamic environment of our body that involves motion all the time? Actually, have people look into this? I did more reading, and I realized that it's not a well-understood problem. I was very excited because I just discovered a new project. In my next group meeting with my advisor, I eagerly told him my finding. He looked at me calmly and he said, "Sounds good. I have two questions. How are you going to test the failure of two-dimensional materials, and what do you expect to learn out of it?" It took me even longer to find the answer. Finally, I talked to him again. "So, how are you going to test their failure?" he asked. "We can do a fracture test," I said. "Normally, this is done on a testing machine that clamps a partially cracked specimen at both ends. The machine then stretches the specimen until it fails completely. However, we cannot use this system to test two-dimensional materials because they are much, much smaller. We need a system equally small. One option is to use a micro-electromechanical system, or MEMS. They are tiny silicon chips with delicate structures on it. This particular MEMS, for instance, is only 1/10 the diameter of a quarter. In fact, the structures on it are so small that we need to use a microscope to be able to see them. They convert electrical signals to mechanical motions that stretch the two-dimensional materials. Because of its small size, it can stretch the two-dimensional material in a very gentle way and will give us enough time to observe how they fail." "Sounds good," he said. "Suppose you can do that. What do you expect to learn?" "Sure," I said. By doing a fracture test, we collect the force to stretch the two-dimensional material as a function of the magnitude of stretch. The first thing we learn after getting this data is the last point, which captures at what magnitude of force and stretch the two-dimensional materials will fail. They will be very important parameters for engineers who design those products, as long as they make sure that the electronics work at force and magnitude of stretch much below this point, the electronics won't fail. Moreover, if we're not satisfied with their current performance, we can use this test to explore strategies that can improve their performance. Sounds good, he said. Now get on to the nitty-gritty and figure out how to do those things. What have researchers learned about their failure? It turns out that, unfortunately, two-dimensional materials are as brittle as glass. In other words, they're very easy to fracture. This issue is currently limiting their application and manipulation. The reason they're brittle is that their structures are too perfect, with few imperfections, such as missing atoms or slipped atom layers. It is these imperfections in materials that make them less brittle. We're currently trying to introduce imperfections into their structures and test how they behave. We hope that by alleviating their brittle nature, more possibilities for flexible electronics could emerge. And they will not only be proof of concepts in the laboratory, but can be applied for real patients. Thank you.